This week we are starting our unit on light waves. So light is considered to be a wave in most instances, so much of what we learned last week will be true about light. Last week we also talked about sound and things that were specific to sound. In many ways, everything that was true for sound is going to be the exact opposite for light. So let's go ahead and review really quickly some of the stuff we learned last week. For instance, there are two types of waves. There are longitudinal waves and there are transverse waves. Sound was considered to be longitudinal. So if they're truly opposite from each other, it makes sense that light would be the other type of wave, transverse. So maybe some of you had difficulties distinguishing between longitudinal and transverse other than the definition that we gave you because we didn't have a chance to demonstrate this in class. So I'm going to kind of review the differences really quick. A transverse wave is much easier to draw. It's much easier to see. It kind of looks like what we picture waves to look like. Let's say these waves are traveling to the right. Well, the amplitude is up or down. So the amplitude would be considered to be perpendicular to the direction that the wave is moving. And if you want, the symbol for perpendicular is this, and that kind of looks like an upside down T. So that's how I remember the difference, is transverse begins with that T, which is kind of the symbol for perpendicular. Those lines are perpendicular to each other. Now, a longitudinal wave is much harder to draw. It kind of looks something like this. There are areas of really, really dense energy and areas of really spread out energy. Here's the dense energy and the spread out energy, called compressions and rarefactions. So it's hard to see, but the amplitude is actually in the dense parts. And the waves are maybe still traveling side to side, so the amplitude is actually the amplitude is acting parallel to the direction that the wave is traveling. And I remember that parallel has a bunch of L's and longitudinal begins with L. So that's how I remember that. Between these two, how I remember the difference of which one is which wave type, longitudinal or transverse, is harder to see? Well, definitely I would say longitudinal is more difficult to see. If you were to make these in class, like on a slinky is what we would usually have you use, or you could use string, but a slinky is much easier to demonstrate. To make a transverse wave, you just kind of wave the slinky up and down or side to side, and you can make these waves. But longitudinal is more difficult to see. You actually have to pull back the little coils of the slinky and then let go, and you can see energy shoot back and forth, but it's not as obvious. So longitudinal waves are more difficult to see. Between these two, sound and light, which is more difficult to see? Well, light I can see really easily, sometimes. At least what we think of as light. We can see light. It causes us to see. Sound you can't really see. So the harder to see wave is going to be sound, and that's also the harder to see type of wave, which is longitudinal. It has to do with its shape, which is also why it's easy for us to see transverse, aka light waves. Other things to remember, and maybe this one was a weird thought for you, but sound actually travels fastest through solid objects. Things like musical instruments or even a table or something you're landing on that makes a noise. You hear it so well because it's happening through a solid object. We create most of our sound through vibrating solid objects. The one place sound cannot travel is space. Well, the exact opposite is true for light. Light travels fastest through space, and we know light can travel through space because we see light from the sun, we see light from the stars, we see light that's very, very far away that travels through space. And then the opposite is true. Sound can travel through solids, so can light, but light will travel slowest through solids. Doesn't mean light cannot travel through solids. Some of you may think, well, yeah, light's hard to transmit through a door, but light can travel through things like glass. So light can travel through solids, but it's definitely much slower through solid objects. So now that we know all of this, let's go through a few things about light, a few of the basic things about light. So light is a wave, and it's still created through vibrations of some sort, but specifically it's vibrating charges. And maybe you remember from chemistry that electrons can move from a high energy to low energy state that causes them to release energy. That can be released in the form of light. That is how light is created. Light is transverse. We already talked about that. Something to know, light is the fastest entity in the universe. We don't know anything that travels faster than light. And something scientists have learned before us, we have estimated the speed of light to be 3.0 times 10 to the 8th meters per second. It is always traveling at that speed in space. Since we know light always travels this speed, we can use this speed in our speed equations. The symbol for speed of light is going to be c. So anytime a problem is talking about light moving, we can assume it's moving at this speed. And if you notice this equation that's given to us, it's just distance over time, which is similar to our old speed equation. It's just distance over time. But whenever we know light is involved, we can assume the speed right here is going to be 3.0 times 10 to the 8th, which is why we have this new, not so new equation. And something to just know, a light year is a measure of distance, not a measure of time. So a light year is how far light can travel in 1 year, which if you think about how quickly light can travel, that must be a pretty far distance. So let's try an actual math problem. How long does it take for light from the sun to reach the earth if the sun is 1.5 times 10 to the 11th meters away? So label stuff. Meters is a distance. We're looking for how long does it take, time. And normally some of you would think we don't have enough information to solve this problem, but since we know light is involved, we can assume it travels at the speed of light, which we learned an equation for that right here. Speed of light is just distance divided by time. Since we're looking for time, I can just go ahead and rearrange that equation to be time equals distance divided by speed. If you need a quick refresher on how I rearranged that, you can really just switch these two for a shortcut, or I can briefly show you the algebra. Just multiply both sides by time to rearrange. I end up with speed of light times time equals distance. And then if I divide both sides by speed of light to get time by itself, I get this equation over here that I made. Or you can use that shortcut. But now that I have an equation, I just plug in the numbers that were given to me. If you do not have a scientific calculator available at home, there are free apps you can download, ask your teacher for more information, or Google it. But now I just plug in this information and solve. And when you type this into your calculator, you get that the time it takes to travel from the sun to the earth is about 500 seconds. Now, normally, you would just leave this number alone. But just in this instance, I'm going to ask you to convert this because 500 seconds is kind of a weird time to estimate in my head about how long that actually takes. So I'm going to convert that to a unit that maybe is easier to understand just because seconds don't really work very well here. So I'm going to go ahead and convert this to minutes. When you type that into your calculator, you get about 8.33 minutes, which means that light from the sun takes 8 minutes to get to the earth. So if for some reason the sun were to stop producing light or get blocked somehow, we would not know for 8 minutes. Again, you want to leave your units in seconds almost all of the time. I was just converting so we can make sense of that number. So light is considered to be something called an electromagnetic wave, and we will go into that more in another video. But there are lots of different shapes of light. There's light that we can see, and there's light that we can't see. But because it is considered a wave, we can use this wave speed equation to calculate things about the shape and frequency of light. You'll notice that this is the exact same equation we learned from our Intro to Waves unit. The only difference is, since we're talking specifically about light waves, we can insert the speed of light for velocity. Now, any electromagnetic wave is going to be considered to be a light wave. So anytime we're talking about electromagnetic wave, we can use the speed of light. Something to pay attention to, since the speed of light is always the same, as your wavelength gets smaller, your frequency gets bigger and vice versa. They are inversely related. How I think of it is a high frequency wave looks something like this, really bunched together, versus a low frequency wave happens less often and is kind of more spread out. A wavelength on this poorly drawn high frequency wave is pretty short, versus a wavelength on a low frequency wave is pretty long. A trick I kind of remember is low frequency, long wavelength, low and long. And then I also think of high frequency as being really high energy happening over and over and over again, really bunched together. So if it's high frequency, it's going to be a very small wavelength. Great, let's practice the math. Microwave ovens emit about 2,450 megahertz is what that symbol is. What is the wavelength of this light? Microwave is considered to be a light wave or an electromagnetic wave, but if you weren't sure, they kind of say at the end of the problem, what is the wavelength of this light? So things I know, I'm looking for wavelength. They give us a frequency because of these hertz, even if they look a little different. And we're talking about light, so I can assume the speed of light is acting here. So I'm going to use my speed of light wavelength frequency formula. That makes sense here. And I'm going to rearrange to solve for wavelength. Divide both sides by frequency. So wavelength is just speed of light divided by frequency. So now I'm going to plug in numbers. Speed of light is always 3.0 times 10 to the 8th. You do not need to have it memorized. It is on your formula sheet, or maybe you need to write it down in your notes somewhere so you have it, but does not need to be memorized. And then frequency, we want to convert to hertz and not leave it in megahertz. Luckily for us, this problem gave us the conversion. And I have a really easy way to convert this problem without actually putting it in a dimensional analysis table. You just multiply the original number by the conversion factor. And that kind of converts the number for you. Plug all of this into your calculator, and you should get a wavelength of about 1.2 meters, or if we want to convert that into a unit that we can understand, about 12 centimeters. So a way to check your math as you go through these is we had a very high frequency number. It was megahertz, which is really big. And we ended up with a very small wavelength. So what we set up here was absolutely true. Whenever we have a large frequency, we should have a short wavelength, and vice versa. If we have a low frequency, we should have a very big wavelength.